Okay, good morning, everyone. Welcome to the third lecture for the summer school on artificial intelligence and machine learning theory and practice. As always, I would request everyone to mute themselves, preferably close their videos. If there are any questions, ask them in the chat. If, for example, you cannot ask the question in the chat, just unmute yourself and ask your question. Okay. So let's start. So today's outline is we would see a little bit of a review of the motivation of machine learning that we saw in the first lecture. And then we will look into linear regression, which is actually the main topic for today. So in the first lecture, we discussed that there are two type of approach to scientific method. One is a model-based design, and the second is a data-driven design. So for the model-based design, we discussed one of the example where, let's say, Newton, by observing an apple falling under the action of gravity, realized that there is a force between two objects with mass, and then he came up with this force. The force of gravitation between two objects is G m1 m2 divided by r squared. And then by observations and things like that, you find the value of this G, and that's your model. Okay. Similarly, by looking at the spectrum of hydrogen atom, which had light at unique wavelengths, the simple atomic model for hydrogen was proposed, which was something like 1 by lambda emitted by a hydrogen atom is something like r times 1 by n final whole square minus 1 by ni whole square. So this is Ni is the number of shell from which the electron is jumping, and Nf is the final shell in which it lands. That's the wavelength of the light would be given by this equation. So these are model-based design. Humans look at a small sample of data and come up with a model for that data. Now, data-driven and learned ways, which is the modern ways, are completely different. They are primarily driven by data. So let's say how would these methods work? So let's say you observe time and distance covered under the action of gravity. Let's say you have some values for this. Let's say at time 0, the distance covered is 0. At time 1, the distance covered is 5. At time 2, the distance covered is, let's make it with some error, 5.1. And at time 2, this is maybe 10, and so on. So you're just given this data. You want to feed it into a machine learning algorithm. You give it time and distance and ask it to learn the relation between time and distance. Okay. You don't postulate any model. You don't say that the relation is probably like this. You just give the data, feed the data to a machine learning algorithm, and it finds out the relation between the input and output for you. Okay. Is this clear? Everyone is on the same page with me so far? Just a simple yes in the chat would do.
Yes.
Thank you very much. So with this, now let's look at some example of linear regression. Some of the slides are motivated by slides from Joseph E. Gonzalez. So what is the motivation for the starting with linear regression? So for me, these are the two important features in terms of explaining them as a first machine learning topic in a class, which is they're easy to interpret and they're efficient to solve. You don't need any high level knowledge of optimization to solve a system of, to find the solution for a linear regression model. And the thing is, they're quite easy to explain because they're, for me, like in some sense, the simplest machine learning model available to us. Okay. So now let's start looking into it. Let's say, what is a linear regression problem? So let's assume that we have some linear process, some process. So y is some function of x. Okay. And you are given data for this. You are given samples of x and y. So let's say something like maybe for 0, x is 0, for 1, x is 1.1, for 2, x is 1.9, and y is 1.9, and so on. You are given this data coming from this process. We don't know what this process is. We just have the data, access to data for this process. So think of it, the example that we saw, the time and the distance covered under the action of gravity. Imagine that you are given just this data. Now these points, this represent each individual data sample. So for example, this might be this point, this might be this point, and so on, like second point, third point, okay? And based on this data, based on these points, you want to find this relation, this line, what this line is, okay? Of course, this is in some sense average. Y is f of x plus some error, because you can see that all the points are not on the line. They are slightly above the line or slightly below the line. But the main information of this data is inside this f of x. We don't really care about the error. We just want to minimize it, okay? So the goal is, given the data, given the blue points, find the red line, which fits the data well on average. Okay, that's the first machine learning problem that we are going to solve. We're going to see how to solve it, how to set it up, and how to solve it. Okay, and this is exactly equivalent to, well, it's not this, let's call it a linear model, something like y is equal to mx plus b, where you don't know m and b, but you want to find it. You want to find the value of m and b, which represent the data given to you. Okay, so a little bit of background. You are given the data samples xi and yi, and the goal is to learn m and b, which would be y equal to mx plus b. So if you put your x and y in here, the error this is minimized. Your mx plus b matches your y perfectly. Okay, so let's say you are given this data, and I ask you, okay, I want a line to fit this data. So in general, how many points do we need in a plane to pass a line through them? How many points in space do we need to define a line? 2. We just need 2 points, right? So let's select any 2 points and pass a line through them. Okay. So does it look like a good fit to the data, this line? So I selected these 2 points and I passed this line through them. Does it look like a good fit to the data? No, it's not, right? Let's select some other 2 points. Okay, I take these 2 points, pass this line through it. It's still not a good fit. Probably a little better than the previous one, but still not very good. Let's take a third set of points, these 2. And now if I pass a line through it, it looks very good. Okay, so now we have a problem, right? For some, if we choose a subset of some points, we can fit a very good line through it. For certain other points, we might not be able to, if you want to model a line just by those points, we might not be able to find a good line. How do we solve this problem? Which point should we look at to find this line? Any guesses? What should we do to define a line such that it's a good fit to all the data, not just a few points?
Excuse me, teacher. For me, in this question, I think we should define a loss function, and if the value of the loss function is the minimized value, I think that loss function could determine how many points would relate to the line that we have found. It's the
Okay,
loss function.
okay, that's 90% correct, we would say. So that's actually the answer. We want to come up with a loss function, which in some way minimizes the discrepancy, the average discrepancy of hypothesis function, the line which you are proposing, and the data that you have. So let's see how we would do it. Let's try to set it up. Okay, so we want to have in some sense an average line which would minimize this loss. So what we say is that given a point x, we would say that we have a hypothesis function. Hypothesis function is a function which, given an input, it gives you an output. Okay, it's a function, it's not a number, it depends on certain values. So basically what I'm saying is that let's say my hypothesis function for a point x is mx plus b. Why do I choose this hypothesis function? Because I know that my relationship is linear, right? So this is my hypothesis function. I say that, okay, if you give me an x, the output for that x would be mx plus b. So now I have xi's and yi's, the actual values of x and I. Let's give them some test numbers, 0, 0, 1, 1, 2, 2, maybe 1.1, 2.2, or not, 2.0, and 3, 2.9, something like that, this data. So now you want to feed this x into this hypothesis function and get a hypothesis function output for it, get an hx. Okay, hxi would be some number, m0 plus b, m1 plus b, m2 plus b, and so on, right? So I'm just taking this x and I'm plugging it here. M and b are unknown. I don't know what these are. Okay. Now, like one of your classmates pointed out, we want this hypothesis function to be close to y, right? We want the difference between your hypothesis function and the actual label to be small. So what I would say is I'd say, okay, let's construct a loss function, j, which would be y minus y of I minus hypothesis function of xi, and you have to sum it for all points. Let's assume that we have n points, right? Because we want the line to minimize the error for all the points, not just one point, right? Okay, so I intentionally wrote this slightly incorrectly. So can somebody tell me what's wrong with minimizing this? If I want to minimize this loss function, what would be the problem? What would be the value of h of x which minimizes this? So if, for example, let's say that you want to minimize this function, you want to minimize this h, what would be, let's assume that you have just 1 point, n is 1, okay? So your cost function is this, y minus h of x, and you want to minimize it. What would be the value of hx which would minimize it? I would say infinity. H should go towards infinity, because as h goes toward infinity, you would get a very large negative number, which would minimize it, right? But then it kills the it kills our solution. We want it h to be close to y. We don't want it to be close to approach to infinity. So to solve this problem, we put a norm on this h. We put a square. We say that, okay, we don't care whether the discrepancy between whether h is above the line or below the line. We penalize them same way. Okay, so that's why we put a square on it. So that's why we use a norm. It's not necessary to use a square norm, but square norm is the easiest one to solve. So now this is your cost function. You're saying that for each of your point, the hypothesis function of x at that point should be close to y, and you have to minimize the average of this for all points. Okay. Another question, what is this hypothesis function of? What does j depend on? What are the unknowns for j? Let me just write it here. From I equal to 1 to n, yi minus mxi plus b whole square. What does this function depend on? What are the unknowns? M and b, just m and b, because we already know xi's and yi's. Okay, so this is a function of m and b. So now it seems like we are going somewhere. We have defined a loss function, and we believe that minimizing this loss function would get us a good fit to data. Okay, let's look at a toy example. Okay, I have 3 points, x equal to 1, y equal to 1, x equal to 2, y equal to 2, and x equal to 3, y equal to 3. These are these three red points. Okay. My hypothesis function, the hypothesis function that I choose is just h of x equal to mx. I intentionally chose the data such that b is equal to 0. How would you make sure that for a data b is equal to 0? You just make sure that the line passes through the origin. Okay. If the line passes through the origin, then it just has a slope. It doesn't have an intercept. Okay. Intercept is 0. So let's write the same cost function that we wrote here for this data. Okay. So this would be j is equal to summation I equal to 1 to 3 yi minus mxi whole square. Everyone is on the same page with me so far? Remember,
Yes.
hypothesis function is just y minus h of x. Sorry, the cost function is y minus h of x. Okay. So now that we have so if you look at it, if I write index here, I here, so I is 1, 2, 3, I is the index, the position of the data. So I have chosen the data such that x and y are both equal to I. Okay, for this particular example. So can I write it like this? I equal to 1, 2, 3, I minus m of I whole square. Everyone is okay with this? I just replaced x with I and y with I because I know that x and y are both equal to I. For this particular example, you can see that I is the index, the position of the data point. For first point, x is 1 and y is 1. For second point, x is 2 and y is 2. For third point, x is 3 and y is 3. So everyone is okay with this? I need at least 30 yeses in the chat before I.
Yes.
Okay, perfect. So let's draw this cost function. Okay. Again, what is this? What is this? What is the independent variable for j? What does it depend on in this case? It depends on m, right? This is a function of m. So let's put m here and let's plot this cost function. Okay. So let's say I find the value of j at 0. Okay. I put m equal to 0. So if I put m equal to 0 here, this just becomes summation I equal to 1 to 3 I whole square, right? I've replaced m equal to 0 here. So if m equal to 0, this term disappears. You just have I square. This would become 1 square plus 2 square plus 3 square, which is equal to 14. Okay, so let's say this is 5, 10, and 15. So at 0, m equal to 0, the cost function is 14. Okay, everyone is with me? I'm just trying to plot this cost function against m. Okay, perfect. Now let's find the value of j at 1. Okay, so this would become I equal to 1, 2, 3, I minus m of I, m is 1, I minus I whole square, which is 0. I've just put m equal to 1 here. If you put m equal to 1, this is I minus I whole square. So at 1, the loss function is 0. Okay, let's do it for j equal to 2. So this would become I equal to 1, 2, 3, I minus 2i whole square, which is minus I whole square, which is equal to I square, which is equal to 14, because we know that summation 1 to 3, I square is equal to 14. Everyone is with me so far?
Yes.
Perfect. So at 2, it's 14. If I keep plotting it, I'll see that the cost function looks like this. Okay. Now these type of cost functions belong to a special class of functions in optimization. And these are very nice functions. Can you tell me why this is a nice function? what is the advantage, what is the benefit of having a function like this in optimization? Just by looking at this figure, what is good about this function? Okay.
Excuse me, Professor,
Yes.
because it has a minimized value that we can find actually. So we think this function is a good function because at least it has a minimized value.
Okay. Um, that's okay. It has a minima, but it's more than that. The thing is, it has a minima and it has only one minima. Okay.
Yes, yes.
Okay. And these functions are called convex functions. Convex functions are the functions which have only one minimum. There's a mathematical definition of a convex function, but I would give you an easy definition. And the easy definition is if you join 2 points on a convex function, let's say you join these 2 points, the function values at every point would be under this line. Okay, so you join these 2 points. So between these 2 points, the function would always be below the line. Does it make sense? Join any 2 points of a convex function, and the function between these 2 points, the function would lie below the line. That's the definition of a convex function. Does it make sense to everyone?
Yes.
Okay. Okay. So this is a convex function. Again, we said convex function is good because it has one minima. Because remember, you can have a function like this. Let's say you have a function like this. Now this has a minimum. This has minimas. It has multiple minimas. This. But it's not very nice because it has multiple minimas. We would see why having one minima is good. Okay. Okay. Now we have set up the cost function. Everything is good. Now let's try to find this minima mathematically. Okay. We know that it has a minima. It has a single minima. Let's try to find it now mathematically. How do we find minima of a function? If I give you a function f of x, let's call it f of m because we are calling our independent variable m, and I'd ask you to find minima of this function with respect to m. What would you do? Okay, first thing is you take the derivative. Let's assume that it's a function of one variable. So let's stick with derivatives. Gradient is when you are in high dimensions, but let's assume that it's a single function in one dimension. So you find the derivative, which is d of f of m with respect to m. Okay, what should I do after that? Okay, you set it equal to 0. You set it equal to 0. Let's say it gives you certain point m0. What else? What do I do after that? You solve this equation, you get m equal to 0. What should I do after that in order to make sure that this is a minimum? Because second derivative can be 0 at a minima or a maxima or a what is it called, point of inflection, where the gradient change is sign. Okay, like somebody pointed out, look at the second derivative, and what should the second derivative be? If the second derivative is greater than 0, it's a minimum. If a second derivative is less than 0, it's a maximum. Okay, and how do you know that? How do you come up with these points? It's not something that you have to remember. Just write the Taylor series approximation of a function around m naught. So if I write the Taylor series approximation of f of m around m naught, this would be f of m naught plus the derivative of f at m naught delta x plus the second derivative of f at m naught delta x square plus order of delta x cube. Okay, something like this. This is the Taylor series approximation of f around m naught. For m naught to be a minima, this has to be 0. Because if this is not 0, you can put positive delta x on one side and negative delta x on the other side, and get a value larger or smaller than f of m. Does it make sense to everyone? So let's assume that this is not 0. Okay, you are at m naught. So delta x here is positive, delta x here is negative. So at this point, at this side, you would have a value greater than f of m naught, and at this side, you would have a value less than f of m naught. Okay, because this is your definition. F of m naught plus derivative of f at m naught delta x. So unless this is 0, you can make the value positive on one side and negative on another side. Does it make sense to everyone? If it doesn't, just say no, it's not clear, and we would look at an example, or we would think about it. But don't be shy, ask questions. Is it clear? If it's clear, just put some yeses in the chat.
Yes.
Okay, perfect. So now let's say that this is 0. Now what should be the second derivative in order for f of m to be greater than f of m naught, because f of m naught is the minima. If it's minima, then around this, all the fm should be greater than this. This has to be greater than 0 because this is a positive number. Delta x square is positive, so this has to be positive in order for f of m to be greater than f of m naught. So that's why we have these points. So this is just simple math. These points for the derivative to be equal to 0 and the second derivative to be greater than 0 for a point to be minimum. Okay. So now let me get another clean page. And now let's do it for the data that we have. So we had this j of m is equal to summation I equal to 1 to 3 I minus m of I whole square. Okay, what should I do? I need to take its derivative with respect to m and set it equal to 0. D by dm of j of m is equal to summation I equal to 1 to 3 d by dm of I minus m of I whole square. Can I take the derivative inside the summation? Can I? I'm looking at the chat. Yes, a derivative is distributed over a sum. Okay, so the derivative of f of 1 plus f of 2 is derivative of f of 1 plus derivative of f of 2. So you can take the derivative inside the summation. So d by dm of j of m is equal to summation I equal to 1 to 3 d by dm of I minus m of I whole square. What is the derivative of I minus m of I whole square with respect to m? What should I do? Okay, so this should remain the same. If I use the product rule of differentiation, this would become 2 of I minus m of I. And then using chain rule, I have to take the derivative of this quantity, which would become minus I. Is this derivative correct? Is it clear to everyone? Okay, perfect. Now let's set it equal to 0 and let's see what happens. So we get minus 2 I minus m of I summation I equal to 1 to 3 is equal to 0. You can take the 2 outside and divide both sides by minus 2. This would disappear and you would get, sorry, there is an I here. You would get summation I equal to 1 to 3 I square minus m of I square and this becomes summation I equal to 1 to 3 I square minus summation I equal to 1 to 3 m of I square. I just took the mi square to the other side. And since m is constant for all three terms, you can take it out. This becomes summation I equal to 1 to 3 I square equal to m summation I equal to 1 to 3 I square. And this, you can divide both sides by this quantity. So then it would give you m is equal to 1. Okay. And this is exactly what we had here. The minima was at m is equal to 1. Is it clear to everyone what I did here? Just took the derivative, set it equal to 0, and solve it for m. Perfect. What I would claim is that since it's a convex function, I do not need to check the second derivative. I know that this is a minima. If the derivative is equal to 0 somewhere, for a convex function, it's a minima. And it's a global minima. Does everyone agree with me?
Yes.
Okay, perfect. So that's the advantage of convex function. You don't need to calculate the second derivative to make sure that it's a minima, and you will not have more than one minima. You will have one minima, which is a global minima. If, for example, you had this function, the function in green, you would have to check because this point also has gradient equal to 0. This is a maxima. Okay, so you would have to check whether it's a maxima or a minima, and then you would have multiple minimas, and you would have to check all of them to find the global minima, the one which decreases the value the most. But here you don't have to do it. For a convex function, you don't have to do it. So now we have a setup. Given any data, we would construct loss function based on the data and a hypothesis function, and then we would minimize that loss function. Okay. One thing which, by the way, I have conveniently omitted is that whenever you look at literature and you look at books, this would always be normalized by 2n, where n is the number of points and 2 is just a normalization constant. I conveniently omit it because this is a positive number, and multiplying a function by a positive number does not change its minimum. It's just like make it bigger and smaller. So my function is like this. If you normalize it by 1 by 2, and it would look like this, but it doesn't change the minima. For me, it's just a clutter, and I just remove it for explaining the theory of regression. But when you look at books, you would see that this normalization factor is always there. So don't get confused by this. Okay, so we have a setup now. Now let's do it for something which is more complex. Let's say we have uh, um, a function, a hypothesis function, which is a function in two variables. Let's say, again, we take some data, x and y. So let's say at 0, y is 1, at 1, y is 2, at 2, y is 3, and so on. At 3, y is 4. So now we see that this doesn't pass through origin. So there has to be a b in a hypothesis function. So I would say that h of x is m of x plus b. This is my hypothesis function. My loss function would become j would become summation I equal to 1 to n. I'm assuming that we have n points, n data points, not just 3 or 4. And you would have yi. Yi represent the ith data point, the y component of the ith data point, minus m of xi plus b whole square. And you would have to minimize it. Again, we do the same setup. Now we have, this is a function of two variables. What do we do when we have a function of two variables? How do we minimize that? For one variable, we just look at the derivative and set it equal to 0. What should I do for a function of two variables? Partial derivatives, okay. So you find all partial derivatives and set them equal to 0. The vector of partial derivatives is called gradient. Okay, so you have to find the gradient of j. So the gradient of j would be derivative of j, partial derivative of j with respect to m, and partial derivative of j with respect to b. So partial derivative is derivative of a function with more than one independent variable, where you assume all the other independent variable to be constant except for the variable with respect to which you are calculating the derivative. Okay, so nothing fancy. When you are calculating the partial derivative of this with respect to m, you would assume b is constant. Okay, so it would be exactly equivalent to like a function of one independent variable. And when you're finding the partial derivative with respect to b, you would assume m to be constant. So it would be exactly equivalent to calculating the derivative of a function with one independent variable. Does it make sense to everyone? Okay. Okay, I'm sorry. Again, I got this message that I have to talk a bit slower because some of you cannot follow. So I'll try to talk a bit slower. So for a function with more than one independent variable, we use gradients. We have to set the gradient equal to 0. And what is gradient? Gradient is a vector of partial derivatives. Okay, you take the partial derivative of your cost function with respect to each independent variable and stack them in a vector, put them in a vector. How do we calculate partial derivatives? Let's say you have this cost function. You want to calculate its partial derivative with respect to m. So apart from m, assume that all the other independent variable apart from m are constant. So when you are calculating partial derivative with respect to m, you would assume b is constant. Okay? When you are calculating the partial derivative with respect to b, you would assume m is constant. Okay, that's how you calculate partial derivatives. Okay? Is it clear to everyone? What do we have to do when we have more than one variables?
Yes.
Okay, I want to see at least 20 yeses before I move forward. Okay, so it seems like more or less things are good. So let's see if we can calculate the partial derivatives. So I'm not going to write all the steps because we just did them, but let's see that if we can agree or not. The partial derivative of j with respect to n would be I equal to 1 to n and 2 times yi minus nxi plus b times minus xi. Is it correct?
Yes.
I just used the same derivative that I calculated in the previous part. And the partial derivative of j with respect to b would be I equal to 1 to n, 2 times yi minus nxi plus b times 1. Is it correct? Is everyone on the same page? Is there any confusion for anyone? Nick, you look a bit confused.
Yeah, because I think it should be -1 instead of 1
Oh,
because
of course, it's -1. Of course, it's -1.
so
Yeah,
yeah, that's what I think.
yeah, it's
Perhaps it's wrong, but I can't guarantee.
yeah,
So
yeah.
that's why.
So it's minus
Okay.
1. That's it. You have the partial derivative with respect to m and partial derivative with respect to b. Now you have to set it equal to 0 and solve this system of equations. So what are the unknowns in this system of equations? In this system of equations, what are the unknowns? M and B, of course, two unknowns. And how many equations do you have? Two. So you have two unknowns and two equations. So if the two equations are independent of each other, you should be able to solve it, right? Because two equations, two unknowns, but both equations are independent of each other, you should be able to solve it. But this can be a bit a bit tricky, a bit annoying. There is an efficient way of doing this. Okay, let's look at the efficient way of doing the same thing without too much trouble, without going through this difficulty. So let's see what we can do. We have a trick which is called vectorization. Okay, so let's see what is vectorization. Okay, so I'm going to take the same data. I'm going to take x i's and y i's. So at 0, y was 1, at 1, y was 2, at 2, y was 3, and so on. We have endpoints. Okay, and we saw that yi is h of xi plus some error, right? Because they do not necessarily have to be equal. If you see this, so you can see that y and the hypothesis function do not have to be equal. They can have some error between them. We just want to minimize this error, right? So if I want to write y in terms of the hypothesis function, I can write it like this. So y is equal to h of x plus some error. And this error I'm trying to minimize. Does everyone agree with this notation? Everyone understands what I'm trying to do? So it's just a notational change. So look at it this way. What was my cost function? My cost function was summation I equal to 1 to n yi minus h of xi whole square. Everyone agrees with this, right? Because that's what we were minimizing, right? Can I
Yes.
call this EI? Is it okay if I call this EI? I just want to rename it. So I'm saying that yi minus h of xi, let's call it EI. I can do that, right? I can call this difference by a variable name. Okay, so then yi would be h of xi plus ei, which is exactly this, what I've written here. Make sense?
Yes.
Okay, perfect. So now let me write these, for this point, let me write this. Yeah, so this would be y of 0 is equal to h of 0, which is mx of 0 plus b plus e of 0, right? So I'm writing this is hypothesis function, h of x0, right? Let me write it for y1. This would become m of x1 plus b plus e1, right? For y2, this would become m of x2 plus b plus e2, and so on. We would have y of n is equal to m of x n plus b plus en. Everyone agrees with this so far? Nothing fancy. I just wrote for each data point, I just wrote this equation. Okay. Now this is a system of equation, and I will try to write it in vector form, in matrix form. Let me just remove this. To make some space. So can I collect all these y's in a vector? Can I write them as a big vector, y0, y1, y2 till yn? Is it okay to do it? Yes, it's a system of equation. You can collect them together. What are the unknowns in these equations? For all these equations, what are the unknowns?
M and B.
M and B. So let's collect the unknowns here. Let's write them M and B. And we will have a matrix here. What would this matrix be? So for y0, what is the equation? It's mx0 plus b. So what is multiplied with m? X0, right? I'm looking at here. What is multiplied with b? A 1.
Yes.
Okay. Plus, we have e0 here. Okay. For second equation, what is multiplied with m? X1. What is multiplied with b? 1. For third equation, what is multiplied with m? X2. What is multiplied with b? 1. And so on. For the last one, this would be xn plus 1. And similarly, we would have e1, e2 up till en. So now I have written the system of equations into a matrix form. Let's just double check that the two hand sides are equal. So let's look at this equation y2. What is y2? It's mx2 plus b plus e. So let's look at y2 here. Y2 is the product of this with this. If I multiply this row with this column, what do I get? X2 times m. So y2 is the product of this and this, which is x2 times m plus 1 time b plus e2, which is exactly this row. So everything is fine. Everyone is with me? Everyone understands how I collected this equation in a vector form?
Yes.
Okay. So now let's call this y. Let's call this a. Let's call this w. And let's call this e. So dash on top means vector or matrix. If it's capital with dash on top, it's a matrix. If it's small with dash on top, it's a vector. And let's see what we can do with this now. Okay, so let's write our cost function again. Our cost function was J was summation I equal to 1 to n y I minus h of xi whole square. And we said that it's exactly equal to ei whole square because we have this equation yi is equal to h of xi plus ei. Everyone is with me so far?
Yes.
Okay, but we know that we have this vector e, which is e0, e1 up till en. Can I write this thing in terms of this vector? What is this? What is the component of each square of a vector? The sum of the square of each component of a vector. What is this? Close, but not exactly equal. There is a special name for it. What gives you the sum of the square of each component of a vector? The dot product of a vector with itself, right? If you take the dot product of a vector with itself, it will give you the sum of the square of each component. Everyone follows that? So what is the dot product of two vectors? I'm not going to call them x, let's call them u and v. What's the dot product of two vectors u and v? This is summation I equal to 1 to n. We are assuming that there are n components of this vector. U of I times v of I. Let me just write it product. You multiply the corresponding components, right? So if you take the dot product of u with itself, sorry, if you take the dot product of u with itself, if you say u dot u, this would be summation I equal to 1 to n ui times ui, which is summation I equal to 1 to n ui squared. Okay, so we can write this as E transpose E. E transpose E is the dot product of a vector with itself. Okay, so this is E. Let's write this. So this is E. What would be the transpose of E? E transpose would be this, right? E0, E1, E2 up till En. And you take its product with E. You take its product with E, which is this, E0, E1, E2, En. You take the matrix product of this with this. This would give you exactly this, I equal to 1 to N, Pi squared. Everyone understands this?
Yes.
Okay, perfect. Let me just remove this. Okay, so now we have this, right? So I can write this as y is equal to AW plus E, right? This is just writing this matrix equations, system of equations, right? So if I want to find the value of E from this, E would be y minus AW, right? Everyone is with me?
Yes.
Okay, let's substitute this value here. Okay, so J, my cost function would become y minus AW transpose y minus AW. And what is the unknown here in this? Look at this. What is the vectors of unknown?
Yeah. W.
W, exactly. So it's W is unknown. We have to find the derivative of this with respect. Notice that the sum is gone. We don't have the sum anymore. Okay? It's just one expression. So let's do this. J is equal to y minus AW transpose y minus A W, and we have to find the derivative of this with respect to W. Okay, so this gives you 2 times A transpose Y minus A W, and you have to set it equal to 0. This is, you can check this, this is an expression of matrix calculus, an identity in matrix calculus. If you take the derivative of so basically, yeah, y minus a w whole transpose y minus aw, you would get this. I've generally memorized it. These are the expression from vector calculus. Okay, so let's. Of course, there is a minus. This is exactly equivalent to that. What we do in a simple equation, the only difference is that you get a transpose here. So if we had to do it for, let's say, when we do it for y minus mx whole square, we get 2 times y minus m of x times minus m. This is exactly equivalent. The only difference is that you get a transpose here. So let's try to solve this for unknown. So this, when you try to solve it, you get A transpose y minus A transpose A W equal to 0, and you have to solve for W, so you get A transpose A W is equal to A transpose Y, and W is equal to A transpose A inverse A transpose Y. this is your solution. You can have any number of bases, any number of data. All you need to do is construct the matrix A and Y, and you will get the unknowns, the best values of the unknowns. Is it clear?
Yes.
Okay. So let's take a simple example. Before I ask you guys to code it, let's get a slide. And let's say I give you some complex data. Okay. This is some complex data, X and Y. So X can be any number. I'm just going to write some random numbers. Okay. And I ask you that, okay, hypothesis function has to be W0 plus W1 times xi plus W2 times x2 plus W3 times x3 plus W4 times x4. Okay, now I have to use a better notation. So let me just clear it and write it in slightly better notation. So this is W0 plus W1 times xi plus W2 times xi whole square plus W3 times xi whole cube plus W4 times xi whole 4. So remember, when I have parentheses, it means power. Okay. And when I have simple superscript, it means index. Is it clear? Do I clear the difference between index and power? So this means ith element of the data. And this means x squared. Okay. Is it clear? Everyone is with me on the same page?
Yes.
Okay, perfect. So now let's write the system of equation for this, because when you write the system of equation, everything else is quite solved. So we would have y0, y1, y2, up till yn here. What are the unknowns? W0, W0, W1, W2, up till W4. These are the unknowns. Remember, in linear case, I'm just calling them M and B. But if you have more than two bases, you would have to call them W0, W1, W2. It's more convenient. Of course, you can call them M, B, K, L, P, whatever you want to call them, but it's better to call them W0, W1, W2, W3, and so on. Okay. So now let's see. What is the weight of W0 for Y0? What is multiplied with W0? 1, right?
Yeah, one.
1, okay. What is multiplied with W1?
Xi.
Xi, yes. In this case, it would be x0 for the first I. What is multiplied with W2?
Xi superscript square.
Okay, x0
Super.
squared. Okay, and similarly, x0 cube. Okay, we have 4 as well, so I have to make some space for it. X03. Similarly, what is the weight for W4? What is the weight for W4? X04, exactly. Similarly, for Y1, this would be 1, x of 1, x of 1 whole square, x of 1 whole cube, and x of 1 whole 4, and so on. So you would see that this, if you have a vector of x, x0, x1, x2, up till xn, you would see that the first column is this vector power 0. It's x vector power 0, because all of these are 1, right? The second column is x vector power 1. This is just the value of x vector. The third vector, the third column is x vector square, element wise. These are element wise operation. Okay. The fourth column is x vector power 3, element wise. And you can see exactly that this is indeed the case. So what is x? X0, x1, x2, x3, x up till xn. What is the second column? X0 square, x1 square, x2 square, x3 square, and so on. So in order to construct this matrix A, all you need to do is take the vector x, take its 0 power, its first power, its second power, element wise, third product and fourth power, and stack them in columns. That would give you A. Okay? And once you have A, you have everything, because W is just A transpose A inverse A transpose Y. Okay? We know how to do matrix product in NumPy. You can use at the rate. At the rate can take the product of uh, two matrices. And for inverse, you can use np.linearalgorithms.inverse. That's it. Everything else you have. Okay. So I'm going to ask you guys to go to chapter 5, try 5.1 and 5.2. Also go to the website on day 3. You will see that there are 3 exercises. One is for the gravity on the moon. I've generated the data there. You have to do the linear regression. One is for the Rutherford atomic model. You have to do that. And there are some other exercises where I've generated data and you have to do linear regression. You have to find hypothesis function h of x in certain basis. Okay, give it a try. You have around 1 hour till 11, and then at 11:30 I will sit with you guys and we will do these exercises. Okay, any questions?
Excuse me, Professor, can you hear me?
Yeah, go ahead.
Yeah, could you go back the previous slides? Because I think you mentioned that you use EI to replace YI minus HI. I actually I don't quite understand why is it so necessary, or why do we need to use EI to replace YI minus HI?
It's just a notational thing. Essentially, we are doing this y minus h of I. If you can write them in direct matrix form, you can use directly matrix form. But I wanted to write them in this form, in this system of equation, and I wanted to have this EI here, and then I wanted to show that this is just a dot product of E with E. So that's why I use this notation. You can directly extend it. You can say that, okay, I'm just going to get an extra slide. If you are comfortable with it, you can directly do this. You can say that since the loss function is I equal to 1 to n, y minus h of yi minus h of xi, you can, if you're comfortable with it, you can directly say that if I stack them, this would be equivalent to y minus ax or aw, sorry. You can do that, it's fine.
Okay, I
You
see.
can do that directly. I just did it because I like this notation to show that this is indeed, this is EI square, and then this is dot product, and then this is Y minus A transpose W, and so on. So this then becomes transpose Y minus A W. So you can write it directly if it's directly visible to you. I like to do it through EI because it's a little convenient to explain for me.
Yeah, I see your point because it's easier to show that E transpose times E. Yeah, I understand what you mean.
Okay.
Thank you.
Yeah. What else? Any other questions? Okay. So give this a try. I know it might be a little difficult for some people, but it's not. It's very easy. Linear regression is like very easy. So give it a try. Spend around an hour. Keep thinking about what we did. Try to derive it on a page if you want. It might help you in setting up your code. And then at 11:30 we would resume the lecture and we would actually code it together and see how it works. Okay. I'm going to stop sharing the screen and pause the recording. I'm available in the chat if there are any questions. Thank you. So recording and we're going to start working. So basically we saw that for linear regression, W is A transpose A inverse A transpose Y. So we just need A and Y. So if we have these two, a matrix and a vector, we can calculate the weights. So the trick is how do we calculate, how do we construct the matrix A? Like I said, that if you have the vector of data X and Y, this would be your input. This is your data. So this is the input, and this is the label, or you can call it output. And we are interested in finding the F or a hypothesis function H, which is quite close and minimize this, quite close to Y and minimizes this error. Okay, so the structure of X A is X power 0 in first column, X power 1 in the second column, X power 2 in the third column, and up till X power M, where you have M is the number of bases that you have. This is A. And that's basically the main thing that we have to construct in order to find the solution of linear regression. Okay, so we have X. Can I use broadcasting in NumPy to calculate this A? The answer is yes. So we have X, the size of X is, or the shape of X is n times 1. Okay. If, for example, I have something for bases, or I should call it base power, if its shape is 1 time m, I take the power of x to the power bp, it would do the broadcasting and return A. Okay. The rest is actually quite straightforward. So I'm going to go to a Colab, Google Colab, and actually physically implement it. So let me share my screen. Okay. So this is my data for the gravity on the moon example. So just a note, the stories or the scenarios that I have come up with, these are not real scenarios. These are just like some fictional scenarios. So don't use them in like a real life anecdote or something like that. These are fictional setups. So we have time, t, which is independent variable, and we have s, which is our dependent variable. So let's first look at the shape of both these variables. So what is shape of t and shape of s? Okay, so this is, t is correct shape, 20 times 1. S is, we need to make it 20 times 1 as well. So in fact, let me do it the way you guys have. So you guys have this data. Yeah, let me just run it. And now let's look at the shape of t. Okay, both of them are 20. They're not like vector form, a column vector form. So the first thing I want to do is I'll call x the column vector version of t. So I'll take t I'll take all rows of it and I'll insert a new axis here. And then y is s, all, all the rows and np dot x's. Now let's print the shape of x and y. Okay, this is good. So now both of them are column vector. This is exactly like we have in our data. Next, we have to construct A. Like we said, x is n by 1, and we want basis power to be 1 by m, where m is the number of bases, right? So the first thing that we need to do is we need to define the number of bases. Let's say in this case, I take number of bases 5. This is a design choice. We would see what are good values for this design choice. Then I can generate BP, which is basis power. You can just simply say np.a range num underscore bases plus 1. Plus 1 because we want 5 bases. I don't call W0 a base. Let's call it a bias. So it's n base, number of bases represent the maximum power of your x vector. So in this case, I wanted 5, so I just added plus 1 here. Let's make it for now, let's 3. Okay. So now let's create this. Let's look at bp.shape. Basis power dot. In fact, let me just write it like this so that people understand. So let's look at its shape, and it's 4 times this. We want it 1 times 4. So I can just do this. Basis underscore power is equal to basis underscore power np dot new axis. And now, so now it would be the right shape that we want. Now A is just x power basis underscore power. Okay. And let's just double check the shape of A. So it's fine. That's exactly how we expect it to be. And let's just simply implement the solution for linear regression. Inverse what A dot T product with matrix product with A, and then the product of this with A dot T matrix product with Y. So I just simply write the expression A transpose A inverse multiplied with A transpose Y. Okay. Everyone is with me so far? Everyone is clear as to what I've done so far?
Yes.
Okay. Any confusions? If any part is difficult, anything is tricky, or something is confusing, feel free to ask at any time. So once you have this, what is T? Okay. So if you A dot T is transpose of A, and at the rate is matrix product. So let's just quickly look at this. Print A dot shape and A dot T dot shape. You would see that A dot shape is 20 times 4 and transpose shape is 4.20, exactly like we expect. Okay. So A dot T is just transport. At the rate is matrix product. Okay. Transpose. Why not A dot T dot A? Because we are looking at matrix product. I don't think that dot is matrix product. Dot. I don't think dot is an operation because dot is used for objects. So let's do this. A dot T dot A. I think it will just give an error. Yeah. Or do you want to write dot? I think even that might not work. Yeah, so I'm not clear, but at the rate is used for matrix product. Okay. So I'm not sure what, I might be missing something. So just write it in a message, probably with a little more detail, and we'll try it. Anyway, so now we have W. So what is our hypothesis function in our representation? Our hypothesis function is AW, right? A matrix product W. Remember that we had this. We had y minus a w, where y is the actual function, actual output, and aw is our hypothesis function. So if you want to find the value of your hypothesis function, just take the matrix product of a and w, and let's plot. Let's plot x and y mu, and let's see how it looks. Okay, so it's a good fit. It's quite a good fit, which means that this linear regression algorithm is good. But let's look at W. What do we expect W to be? So remember, let's look at the question. So the question is, we are finding the value of gravity on the moon. And we know that the gravity of the moon is 1/6 of the gravity of the Earth. So the equation of motion is S is equal to half g t square. So technically, W is this should be 0 because this is the weight of x power 0. There is no constant offset. So let me just write it. So the function, the actual function, f of x, or in this case, f of t, is just 0.5 times 9.8 divided by 6 times t square, right? It doesn't have anything with t power 0. It doesn't have anything with t power 1. It doesn't have anything with t power 3. It just has t power 2. So this should be 0. This should be 0 or very close to 0. And this should be 0. But we see that it's not, right? These have some values. Can somebody tell me why this is the case? The answer is here. Why don't we find the value exactly? Why is there this little offset? Yeah, exactly, because we have some noise, okay? Let's make the noise small and let's see if we can make things better. So I have decreased the noise, and where do I start? I think it's here, yeah. Let's run all of these again. Hopefully it would be better now, and it does indeed get a little better. You can see that the majority of the weight is here, and these numbers are quite small now. We want this one to be equal to 0.5 times 9.8 divided by 6 to be equal to 0.816. This should be 0.816. All the other ones should be quite close to 0. Let's put exact 0 and let's see if that works. Okay, so now we have an exact function. And now it works. You can see that these are 0, literally, right? 10 to power 12, 10 to power 12. And this is 8.166. Exactly this. Okay? So linear regression works. It can find you an unknown function. Okay? Let me just clean this code up, collect everything in a single block of code so that we can go through them in an effective manner. So I'm going to remove the unnecessary comments and prints. So you can see that the entire linear regression code is just 10 lines with plotting and data reshaping and everything, 10 lines. And that's your first machine learning algorithm. Okay. Basically, given any data, we can find the relationship between the input and the output. Okay. This, by the way, was very simple data, right? It's a very simple relationship, but I just wanted to use it because it's just interesting. We looked into it. There are better examples in this notebook, tougher problems. You might need to use more bases, things like that. So should I just copy the code from the previous notebook, or do you guys want me to rewrite it so that we can have a revision of it? Up to you guys. Just mention in the chat what you want. Should we rewrite the code or just copy it from the previous notebook? Okay, one vote for copy. Okay, let's just copy it from there. I would have preferred rewriting it because I think it gives a good revision to the student, but if you guys are comfortable, I'm comfortable too. So let's just copy it and bring it here. So let's see if we can learn cosine function from here. So I would have to make slight modification because I call it x and y here. So probably this becomes x and y. Everything else should remain the same. I don't think anything else needs changing. Let's run it. Okay. Let's run this. Okay. It doesn't fit very well. Can somebody tell me why this is the case? Why it doesn't fit well? What do you think is the reason? Yeah, the order is too small. We don't have enough polynomials, right? So basically right now, I'm just saying this. I'm saying that the function is f of x is w0 plus w sub 1 times x, I should put times, plus w sub 2 times x square plus w sub 3 times x cubed. Okay, so just three bases. This is not enough for sinusoid. So let's make it 5. Let's see what happens. Okay, so now I have an issue because you can see that it, I think, puts another x's. So let me see what I can do to make this better. So if I do this, x0 and y0, save it and run it, and then let's call it x0 and y0. Now I think it should be fine. Okay, this is x0 and y0. So one, of course, x0. So basically, since I'm inserting an x's here, if I run the code again, it would put another x's in it, and then the shapes get bad. So I should not say, this is not a good practice to say x is equal to x new x's, because every time it would just add a new x. So it's good to have two different names for the two variables, and that's what I'm trying to do. I'm calling this the original data x0, y0, and then when I insert the extra x's, I'm calling them x. Okay, okay, not very good. Let's make it 7. Okay, let's make it 11. Okay, let's make it 15. Okay, it's getting better, but not extremely better. Let's see if I can make it a little better by decreasing the noise. We will, by the way, see how to make, this is because this is an elementary class, we are not looking at regularization. So I'm making the function a little better. And tomorrow we would see when, if the data is bad, and let's say certain number of bases are not working, what to do to make it better. There are some techniques, but we haven't studied them today, so I'm not using that. I'm just trying to make the function a little better so that it can fit to it. Okay, 15 is too much, probably 9. Okay. Make sure that everything is in order. Yes, it seems fine. Number of bases, 8. Okay. Decrease the frequency a little. Okay. Now we're going somewhere. Okay, a little better. And let me see what the function is. It's a very small noise. It should fit it almost perfectly. There shouldn't be any issue. I have to just look at my code once more to make sure that I'm not making any errors. Okay, so eventually for certain bases, you would see that it captures it perfectly. You have to increase the number of bases, find the right position. Generally, we will find a technique where you can give a large number of bases without running into the problem that comes with the large number of bases. But you might need to play with this number. So now you can see you didn't tell it what the function is. You just give it data, x and y. You see this block where I'm finding the function. I have access to just x and y, and I can find the function, whatever it is. Okay. So let's do it for another function. What is this one? Okay, this is a noisy step function, technically very difficult to handle. Let me just make it a little easy. So let's make it 1. Okay, and probably let's make this a little small as well. Okay, this is a little better. 0.5 maybe. Okay, so this is a fine function. Let's try to um, to perform linear regression on this and see what happens. Okay, so let's good. Let's copy it here. Everything should work fine. Okay, so this is a good fit. You guys might think that it's not amazing, but it's a fine fit. I'll explain why you cannot expect it to be much better than this. Okay, but this is a fine fit. Let's leave it for tomorrow. Why we can get things better than this, but let's give it something like 21 and let's see what happens. Okay, so you will always have these ripples, and I'll explain. We will see why this is the case. Anyone who has a background in signal processing might know it already, that this things happen when you have discontinuities in your function. Okay, we will have a look at it tomorrow. So let's try this. We have a log, and so this is, by the way, the things that we are doing, it's very naive linear regression. There are some better techniques, but let's delay them till tomorrow. Today, just practice and let's do it with normal, well-behaved functions and try to see what we can get from them. So this is a log with some noise. Sorry. And this one, well, fits quite well. I think it might be able to fit it well with a small number of bases. Okay, and this is a good fit, a very good fit. And I'm not going to do all of them. You guys can do the rest, but what I want you guys to do is be very comfortable with this. Like if I give you any data, you should be able to like implement this very small piece of code to find the linear regression solution for um, any data. The thing is, the beauty is that, see, what we did was we get any random data. We don't know where the data is coming from because we don't have access to this. I'm not looking at this in the solution. I'm just looking at the data, X naught and Y naught. And based on that, based on the tools that linear regression provides to me, I can learn the data quite well. You can see that my learned data, the learned function matches the original function quite well, which is quite nice if you think about it, right? That's basically the essence of machine learning. Here we are doing it on a very small scale problem, but you can extrapolate it to be as large as you want. So image classification is exactly the same thing. You want to learn a function, a hypothesis function X, which takes in an image and say that this is a cat. You're doing the exact same thing, but on a larger scale. And we will do it. We will go in the second week. We will try to classify images, but it would be the essence would be the same. Okay. So try to get comfortable with linear regression, do all the examples, do all the code. I will share this code, my code, at the end of this lecture. It would be on the website, but please try to write your own code. It's just 10 lines, right? And you have seen how I do it. Try to do it and try to run it for all the examples for today's lab. And tomorrow we would try to look at linear regression in 2D, in more than one dimension, linear regression with non-polynomial basis, and regularization techniques. What if you have like this very high frequency thing? We thought that when we had like high frequency cosine, there was some issues. How do we fix those? How do we make linear regression better and like avoid these problems? We'll have a little bit of discussion of overfitting and underfitting. And tomorrow we will close linear regression. Day after we will do logistic regression. So by the end of week 1, we would be done with completely with regression, and we will start neural networks and convolutional neural networks in week 2. Okay. I'll leave you guys to it now. You have around an hour. Practice these codes. Just get very comfortable with linear regression. If you want, it might be better to have a read of the chapter in the handbook, in the course handbook. That's going to be helpful as well. And if anybody has any questions, I'm available in the chat. Thank you, guys. I'm going to stop sharing my screen now, and I'll be available in the chat.
Excuse me, Professor.
Yeah, go ahead.
I wanted to ask one question, not about this algorithm, but about the homework. What I want to know and want to make sure is that are all the exercise we must submit in the end of the course compulsory, or we can choose some interesting exercise so that we. I just want to know, should we finish all the exercises and submit all the codes in the end of the course?
So basically, I'm not going to grade you guys. So it's good if you share everything, because I might give you some comment like, okay, you did this, you can make it better, things like that. But you don't need to submit everything. For example, if you couldn't solve a few exercises, that's fine. So don't worry too much about like, oh, I finished 5 questions, 2 questions are left. It's fine. Just do as much as you can, as much as you're comfortable with. Don't burden yourself too much. Share it with me at the end of the course, and I might give you some comments. I might say like, oh, you have done this very well. This was very nice. This needs changing and things like that. But it's up to you what you want to share at the end of the course. Just make sure that for each day you have something so that I can mark your attendance, because I will mark your attendance based on your homeworks. But you don't need to complete everything. That's fine.
Okay, thank you, Professor. And by the way, I also want to know, will those codes relate to the attendance only, or it will be measured as the score of the certificate, or it has a, could you understand what I mean?
I don't plan on giving you guys grades on your certificate. It would be just like you attended this course and you completed it.
Okay, thank you.